Okay. So welcome back. So I'll be talking now about complex Hessian matrices. Right? In the previous lecture, we talked about complex gradient vectors, and you understand now how to differentiate functions of complex arguments relative to the complex argument. So let's now take this a step further and talk about Hessians. Okay, these are second order derivatives. Okay, second order derivatives, just like you take a function f of x, you differentiate it once relative to x and then twice. Okay, so we're going to take this a step further. Okay, so there is more to say here. Okay, so this material is based on Appendix B from the notes. Okay, so you can just read that appendix if you have questions. Okay, so I'll be talking about Hessian matrices. So these will consist of second order partial derivatives. Okay, from now on, I'm going to focus on real valued functions. Actually, for most of the course, that will be the case because our cost functions will be real valued cost functions. Whether they are quadratic functions, logistic functions, they will be real valued functions, okay? Where you will have complex entities will be in the argument, the z. That can be complex. But the function itself, for example, g of z equals the norm of z squared. That's real, but z can be complex, right? So that's why I have to introduce complex gradients and also complex Hessian matrices. So just keep in mind that from now on, most of the time, the function will be real valued, okay? So what do I want to do now? I want to define Hessian matrices, right? Second order derivatives, right? Of the function g of z. So I had g of z, and when z is a column and I compute the gradient relative to z, I get a row, right? Now I'm going to take the gradient and differentiate the gradient again. Okay, I'm going to differentiate the gradient again. Okay. What you are going to get, so now I'm going to compute a Hessian matrix and I'm going to show you the notation, okay? What you are going to get will be a matrix now. Okay, will be a matrix. So I'm going to define that matrix and what the size of that matrix will be, okay, and what the standard notation. We are also going to be using an inverted delta, okay, for the Hessian matrix with a square symbol. But before I get there, let me first introduce other notation that will motivate that one. So let me first start with the case when z is real. Why? Because it will help me motivate what will happen in the complex case. Okay, it will make it easier for you to follow what will happen in the complex case. Just like when I studied gradient vectors, I said replace z by x and y, right? And then differentiating g relative to z involved partial derivatives relative to x and y. That helped you get an idea of the argument, right? Same thing here. Let's start with a function, g of z, where z happens to be real, okay? So z is real. And it's a vector. Let's start with the vector case, okay? So what is the Hessian matrix? Okay. So what was the gradient vector first? What was the gradient vector relative to z? The gradient vector relative to z was a row vector, right? Which contained the partial derivatives relative to the individual entries of z, right? And you have several of them. Now the Hessian matrix will be m by m, and it will be a matrix that contains second order partial derivatives in it. That's it. It will contain second order partial derivatives. So it's easier to see an example. Okay, so let's take an example. Assume your z has two entries. So z is two-dimensional, right? So the gradient relative to z will be a row vector, two-dimensional, contains the partial relative to z1, partial relative to z2, fine? What about the Hessian? It will be 2 by 2. M is 2. It will be 2 by 2 in the real case. And it will contain all the second order partial derivatives. Second order relative to Z1 relative to Z2 on the diagonal, and then the cross partial derivatives across the cross diagonal. Understood? That's what it is. This is the Hessian matrix, okay? So it's not difficult. This is written down here for a two-dimensional vector, and then I have another example soon for, I believe, four-dimensional vector, okay? Now, it's not difficult for you to observe that to get the Hessian, I can arrive at it in a different way. I can compute the gradient first, relative to Z, followed by gradient computation relative to Z transpose. Or you can do it the other way around. The gradient relative to Z transpose and then relative to Z. This first gradient relative to Z gives you a row vector, right? And then the second gradient relative to Z transpose, it's what's going to give you, the matrix. Fine, understood? Okay. You understand this? Okay, very good. That's one property, and the other property is that the Hessian matrix is always symmetric, right? Go back, look at the 2 by 2 case. This is symmetric. If you transpose it, this quantity is the same as that, right? So the Hessian matrix is symmetric. Okay. So why are Hessian matrices useful? Because once you find a stationary point, how do we find a stationary point? You find a point Z where the gradient vector is 0, right? That's how we define stationary points, right? Find a point where the gradient vector is 0. Let's call it Z0. How do I tell whether that point is a minimum or a maximum, or a local minimum or a local maximum? You look at the Hessian matrix. If the Hessian matrix is positive definite at that point, then it's a local minimum. If it is negative definite at that point, meaning all eigenvalues are positive here, all eigenvalues are negative, then it is a local maximum, right? So this is one useful property of the Hessian, which we will be using later because we will be minimizing cost functions all the time in this course, okay? So that's why Hessian matrices are useful. So let's do an example. What's the gradient vector relative to Z? C is symmetric. What's the gradient vector relative to Z? Just to see if you remember. A transpose plus B transpose plus 2C, right? So the gradient, okay. What about the Hessian matrix? Okay. Okay. You see, you can think about it, again, you can go back to the definition and compute the matrix of partial derivatives relative to the individual elements. You can do that, right? Or you can use some of the remarks I mentioned, because you see the gradient vector relative to Z of G of Z, you just said is A transpose plus B transpose plus 2 Z transpose C. And now, how do you get the Hessian? You compute the gradient relative to Z transpose of this quantity, right? So if you compute the Hessian, the gradient relative to Z transpose of that quantity, the first two terms disappear. Z transpose disappears. What do you get? 2C. Remember this 2. Don't forget this 2 because it will come up in our expressions, and at that time you may ask where this 2 came from. So the Hessian matrix has the 2 in it, okay? In the real case, okay? Fine, easy, okay. Here it is. So now let's go a step further, okay? The complex case, okay? So let's assume now that Z is complex. What will be different now is the Hessian, what was the size of the Hessian matrix in the real case? M by M. Here, the Hessian matrix will be of size 2M by 2M. And for you to understand why, G of Z in this case is G of XY, right? You replace a complex variable by 2M real variables. So that's one way for you to understand why the Hessian matrix is bigger. It's twice as large in the complex case, okay? Let's find out what the Hessian matrix is. There are two ways for you to introduce the Hessian matrix, okay? I'm going to introduce it by transforming z to xy, right, and working with the real arguments. Why? Because I already know how to define the Hessian when I have real arguments. Fine. That's one way to do it. And then the second way, rather than transform z to xy, I'm going to transform z to z star. Okay? And define the Hessian using z star, and you're going to see the connection. Okay? Let's first do the first case because it's easier to follow. Okay? And then I'll make the connection with the second case. So z is complex. Z is complex, so every entry of z has real part, imaginary part. I collect all the real parts into a vector. I collect all the imaginary parts into another vector. So this is x, this is y, right? So this is like writing the vector x, z is x plus j, the vector y, right? The same thing. I'm just telling you in great detail where the entries of x and y come from, right? Okay. Here it is. So your function of z now is simply a function of xy. And you know now how to tell me what the Hessian is of this function of the real variable xy, right? It's actually this, if you want even to be more explicit, this is a function of a real variable, I believe I call it v, where v is column xy, right? If you put all these real quantities into a single vector v, g is a function of v, right? Hessian relative to v will be the Hessian matrix we are looking for. Understood so far? And it will be 2m by 2m. So let's do it slowly. Here it is. This is the first. I call this form the real Hessian form. Okay. The second form, I call it the complex Hessian form. And then you will see the relation. Why do you introduce both of them? Sometimes it's easier to see the structure in one way or the other way. Okay. So g is a function of xy. What is the Hessian? Well, it will be a 2m by 2m matrix containing all the partial derivatives relatives to all the x's and all the y's, right? That's it. I'm giving you an example here. Z is a scalar, but complex, right? But g of xy will now be a function of 2, right? The vector here has size 2, xy. So the Hessian will be 2 by 2. So even when z is a scalar, it's 2 by 2. So 2m by 2m, right? Okay. But it is the Hessian matrix that you get by treating g as a function of xy. This is very simple. You all see that, right? Okay. Continue. Okay. This is another example. What if I have z has dimension 2? So you have a z1 and a z2. So in the real case, I now have 4 variables, right? x1, x2, y1, y2. So the Hessian matrix will now be 4 by 4, 2m by 2m, right? It will be this matrix which has all the partial derivatives, right? You see all the partial derivatives relative to the x1 components, relative to the y1 components, and relative to the cross components, x1, y1, x1, y2, x2, right? This is what the Hessian. So see how I organized it? Okay, because now, so far, trivial extension of what we did in the real case. Okay. I organized it such a way that up here, right, you had all the partial derivatives relative to the x's. So you can get them by computing the gradient relative to the x, then the gradient relative to x transpose. Down here you had all the partial derivatives relative to the y's. And here you had relative to the xy and the transpose of it, right? So why it's useful to write it this way? Because you don't always want to go back and compute the Hessian matrix by computing the partial derivatives relative to all individual entries in your problem, right? So it's useful to know the structure, and that you can compute it by using gradient calculations, which you now know how to do. That's it, okay? So the Hessian matrix is, right, is twice as big, and you see where the size comes from. And this is just short notation, okay? I just, rather than writing this, so differentiate relative to x, right? This means this, okay? What comes first, what comes next. This is just notation, okay? Okay. Here it is. This, I'm just defining the notation which you have it from before, okay? Very good. So that's one way of writing the Hessian in the real case. Differentiate relative to x and y, right? These 4-block Hessian, a Hessian relative to x here, relative to y here, and the cross gradients here and there, fine? Okay. Now another way to write this problem is rather than thinking of x and y individually, lump them together into a vector v, fine? To a vector v. Then, the matrix I showed you before actually corresponds to computing the gradient relative to v followed by the gradient relative to v transpose, right? Okay, you understand? Because this v is like this, a column, right? By definition. So when you compute the gradient relative to v, you're going to get a row. The first part of it will be the gradient relative to the x component that's in v. That is the gradient relative to the y component that's in v. And now you compute the gradient again relative to x and y, then you will get these 4 blocks, right? So this is just another more convenient way of expressing the Hessian, fine? Are you following? Okay. And the Hessian is symmetric. That's all equation 18 is telling you, that the Hessian matrix is a symmetric matrix, okay? So you see that I have 2 ways to express the Hessian matrix in the real form. This is a compact form. Just compute successive gradients relative to v, or define the 2 by 2 block matrix relative to x, relative to y, relative to x and yx, right? So 2 equivalent ways. Very good. Okay. Again, why are Hessian matrices useful in this case, in the complex case? Because if I find a stationary point, a point for which the gradient is 0, then again, right, that point, z0, corresponds to some point v0, and I'm back to the real domain, right? I am back to the real domain. So this property, which I know holds in the real domain, will hold here, right? So if the Hessian, this Hessian that I computed at v0, at x0, y0 is positive definite, then this is a local minimum or it's a local maximum if the other condition holds. You get it? Right? Okay. So far, similar to what we did before. Okay. So let's take this a step further. Okay. So far, the Hessian matrix was expressed in terms of v's and x's and y's. But I would like an alternative representation where, if I'm computing Hessian relative to z, I want all the expressions involved to be relative to z, right? Keeps everything consistent. So this second form will do that, okay? So let me show you. So this is called, this second form, I'm going to refer to it as the complex Hessian matrix. Before I denoted it by HV, this one I'm going to denote it by H sub C, and I'm going to show you the relation between them. Sub C for being complex, and it will be a function of Z, not a function of A. This will be expressed purely in terms of the complex variable, whereas the previous one was expressed in terms of V or X and Y. Fine? Okay. Now, of course, it will have the same size. It will be 2m by 2m just like before, except that the entries, how do I find the entries of this Hessian matrix? The entries of this Hessian matrix are defined in a very similar way to the way H of V was defined. It is also 2 by 2 block. Before I had Hessians relative to Z, Z relative, if you remember, X, X transpose, Y, Y transpose, Y, X, X, Y. Now you only see Z's, right? This is the Hessian relative to Z, Z star, meaning you compute the gradient relative to Z followed by Z star. That's what the notation means. Here, Z, but then you follow by Z transpose. Okay, Hessian relative to Z transpose in the complex case is different from the Hessian relative to Z star, right? These are different variables, right? Okay, and similarly here, you compute the Hessian and you transpose the result. You compute the Hessian and you conjugate the result. What this symbol star means you transpose the matrix and then you conjugate every element in the matrix, right? That's what this symbol, if you have a matrix A, then A star means you compute the transpose of the matrix, and in addition, you replace every entry in the matrix by its complex conjugate. That's what the star operation means, okay? Okay, so now, I'm defining the complex gradient like this. So how is this related to H of V, right? I'm defined it like this, okay? It is related to H of V as follows, okay? I'm showing you first some examples. H of V was symmetric. H of C will be Hermitian. Remember this, when a matrix is equal to its complex conjugate, it means we call it Hermitian, right? Hermitian. Hermitian, okay. So the complex Hessian is a Hermitian matrix. The real Hessian is a symmetric matrix, fine? Okay. And this is just an example. Let's say when Z is a scalar, it will still be 2 by 2, and you will have the derivatives relative to Z, Z star, the conjugate of that, Z, Z transpose, in the scalar case, Z transpose is Z, right? And then here I think it was, what was it? Okay. That conjugate Z transpose, okay. No, sorry, here, right, so that's Z squared star, okay, fine. These are just examples, right? The important thing to notice is that in this complex form, all the partial derivatives are relative to Z and Z star. Very good. So now, how is this related to the previous Hessian definition, right? The previous Hessian definition is what you would normally get as a natural extension of the real case. So how is this related to that? So let me show you. First of all, I can also express this complex Hessian more compactly rather than as a 2 by 2 block matrix. I can express it as a single expression like this involving two successive gradient operations if you introduce this bigger vector U. Over there I introduced V, X, Y. If I introduce this bigger vector U, which contains Z, so Z is a column, Z star would be a row, so I have to transpose it to become a column, right? So this is Z, right? You'll have all the entries of Z, and underneath it, you will have all the complex conjugate entries of Z. So this is a big vector. If you define this U, then the 2 by 2 block matrix I showed you before, you can get it either by computing this succession of gradient calculations. You see here, relative to U. This will give you relative to Z, and then relative to Z star transpose. And then you compute the gradient, right? And you will get the 4 block entries, okay? Fine, you can check it. It's not difficult to check. Okay. So this is the same as HC of Z. I write Z here and I write U here because now I'm expressing it in terms of U, okay? So what's the relation between them? H of V, all of you accept it, and it is useful because once I find a stationary point Z0, I get its X0, Y0, its V0. I can check whether it is a local minimum or a maximum. So if I can show that HC of Z or HC of U, which is the same thing, the complex Hessian can play a similar role, right, then that resolves the issue. Actually, this is a homework problem. You can show simple calculation that these matrices are related in this manner. Okay, so this matrix D, I have it defined, I think, on the next page here, II, JI minus JI. So this matrix D is II and JI minus JI. And this matrix D satisfies this property. Okay. If I did not have a 2 here, this would be a unitary matrix, right? D star equals I. It would be a unitary matrix, right? If I did not have the 2. What would be the inverse of D? D star, the inverse of D star D. But I have a 2, right? if I have a 2, for example, you can see here that D star is 2 D inverse. It's almost D inverse, but not quite, right? Okay, so if I come back here and replace D star by 2 D inverse, what do you get? You get 1/2 D H of V D inverse, right? Okay, I would like to erase this, okay, and write it like this instead. D 1/2 H of V D inverse, correct? What does this mean? I have two matrices here, the real Hessian and the complex Hessian, scaled by 1/2 here, related by a matrix and its inverse. What do you call this transformation? Similarity transformation, right? So similarity transformations do not change eigenvalues, right? So for example, if H of V is telling you that a particular stationary point is a local minimum, meaning all the eigenvalues of H of V are strictly positive, the same thing will happen for the eigenvalues of H of U, and similarly for local maximum, right? So this relation tells you that you can use either H of V, the real Hessian, or the complex Hessian to answer that question. Understood? Okay. So I already showed this. Okay. So that's where I get these statements from, right? You deduce them from the equivalent statements in the real domain. Okay? Very good. So now if you put these things together, this is the conclusion. Okay? If you want to compute the Hessian relative to a real argument, you simply compute a succession of two gradient calculations. Okay, you compute the gradient relative to Z followed by the gradient relative to Z transpose. If you remember, in the quadratic real case, when we applied this, you ended up with 2C, right? In the complex case, there are two ways that you can use to write down what the Hessian matrix is, okay? Two ways. One using the variable V, and the other using the variable U, okay? One using U and one using V. So either you have gradient calculations relative to V and then V transpose, or relative to U and then U star. Okay? Fine? We are going to see some examples, which we are going to revisit later, but now, okay, this will be the standard notation. I didn't want to show it earlier because I wanted you to see these details that. So this will be the notation for the Hessian, the same inverted delta but with a 2, okay? And what does it mean? If your argument is real, it means the first sequence of calculations, gradient relative to Z, then relative to Z transpose. If your argument is complex, gradient relative to U, then relative to U star, okay? So that notation means this, okay? And in the real case, the Hessian will be M by M, and in the complex case, it will be 2M by 2M. Okay. So let's do an example. So let's take here. So G of Z, this is real, okay? And X squared plus Y squared. Now remember, what would be the size of the Hessian matrix here? Z is a scalar, so it will be, Z is complex and scalar, so it's 2 by 2. Okay. If I write it in the real domain, I can write H of V in the real domain or in the complex domain. So the real Hessian, okay, will involve the partial derivatives relative to the X and Y components. The second derivative relative to X will be the 2 here, relative to Y, relative to X and Y, right? So you get this, okay? Here, you have to compute the derivatives relative to the Z's, right? Relative to Z followed by Z star, you get 1, right? Relative to Z star followed by Z, you get 1. And relative to Z followed by Z, you get 0, right? So that's how you get these matrices, right? And you can see that they are related. They are not the same, but that D matrix relates them. The D matrix I showed you before transforms one to the other, okay? So this example is simple. Okay, this is another example. You can do the calculation, right? This is another example. Again, g of z is real valued. Okay, you can compute. In this case, how many complex variables I have? So z is two-dimensional, right? z1, z2. Z is two-dimensional. So the Hessian will have to be 4 by 4. You can compute the real Hessian. You can compute the complex Hessian. This is what you're going to get, okay? And I write h sub c just to emphasize that in this particular case, it's independent of u, a constant, right? Okay. Now, I think this second example is important because it will come up many times in our work, quadratic functions. Quadratic functions. You will do other examples in your homework, but this is a quadratic example. What is the gradient relative to z? Okay, let's first decide which gradient we are which Hessian we are computing, okay? The complex Hessian. The complex Hessian, right? So the complex Hessian, okay, has 2 by 2 blocks, right? So here you compute the Hessian relative to z, then relative to z star. Relative to z, the gradient relative to z, you get a star plus z star c. And then relative to z star, you'll get c here. Right? Okay. And here it is the other way around. Relative to z star first, and then relative to z, and you transpose the result. So you will get c transpose. Here, or here, you compute relative to z and then relative to z transpose, right? If you do that here, for example, this is relative to z. And what is the gradient relative to z transpose? You'll get 0. Because z and z star, okay? So in this example, you will get 0. So the important thing that I need you to remember from this example for later use is that the Hessian matrix of the quadratic cost function is block diagonal of size 2m by 2m. It was 2c there, in the real case, 2c. Here it is C transpose, okay? Block diagonal, okay? And from here you can see right away that in order for me to tell whether I have a minimum or a maximum for a quadratic cost, I just need to examine the inertia, right? This only of C. I don't even need to worry about C transpose. Now, for this example, if you compute the real Hessian, you get the matrix that you have here. So you see, for this particular example, it's easier to work with the complex Hessian than to work with the real Hessian, right? Okay, you understand? So this is one particular example, okay? So here I'm just emphasizing the point I mentioned because it will come up many times. Remember, and this is one of the subtleties that come up when you study complex data over networks. Complex data over networks. Okay? And the issue is this. When we study how information flows over networks, we are going to derive difference equations that tell us how information is flowing over the network. These difference equations will involve Hessian matrices. Hessian matrices will appear in them. As you just saw, Hessian matrices are 2 by 2 block matrices. They contain 4 blocks, right? It's not always the case that the off-diagonal blocks will be 0. In the quadratic case, they are 0, right? In the quadratic case that we just computed, you got C transpose. But in general, these do not need to be 0. When the Hessian matrix is block diagonal, what will happen is, you see, when we study how information flows over networks, you are going to get some equations. Of course, I'm not going to write the exact equation here. I just want to convey the idea. You will get some equations that, let's say, tell you that some quantities A and B, let's say, will propagate according to some equation that looks like this, where you have the Hessian matrix here. So if the Hessian matrix is block diagonal, the evolution of A and B decouple, right? They evolve independently of each other, right? If you have a block diagonal matrix driving the evolution, they decouple. But if you have a full Hessian matrix that's not necessarily block diagonal, then they become coupled. Whatever is happening to A depends on what happens to B and vice versa, right? Okay, so when you study optimization or adaptation problems over networks that involve complex data can introduce some coupling between the evolution of variables in the network because of this problem. Okay, so this is an issue that comes up when you study complex data. It's not just, a trivial extension from the real case. Some issues come up that need to be addressed, okay? And that's why I wanted to stress this point, because you are going to see it in the analysis later, okay? So this concludes this lecture, okay? So before I end it, do you have any questions? Followed everything?
I have a question about
yes.
General, what about homework projects, INFERENCE from the
Okay, very good. Now, do you all have access to the course website? Should all have access to the course website. Okay. On the course website, I uploaded a syllabus for the course, okay? And so what I'm over there, I already have 3 homework assignments, just like 210A. You will have assignment A, assignment B, assignment C. They are due at the end of the course. You'll be getting regular solutions to these problems, so please make sure that you try the problems, okay? And the problems are extracted from a list of problems that I also uploaded on the website, okay? So homework, that's homework, okay? So the course will have a final examination, a take-home final examination, but it will also have a project. So I would like you to divide yourselves into groups, okay? They don't need to be too small. They don't need to be too large. I'm hoping to have about 4, maybe at most 5 projects, so that one day would be enough for us to come here, right? If each one of you can have 15 or 20 minutes, okay? You can go through your project presentations, and I have suggestions for projects in the syllabus, or you can just stop by my office hours and we can chat about ideas for projects, okay? And I can give you some references and so forth. So so that's one thing I would like you to do, okay? And the videos will be posted online. So if for some reason you miss a lecture at some point in time, you can go and watch the video, okay? Any other questions? If for some reason you don't have access to the course website, send me an email, okay? Send me an email. Fine. Any other questions? Okay, so today was the review material, right? Some of you already saw some of this in 210A, maybe not in this detail. The next lecture will be review material plus perhaps some new material, and then we will go deeper into the course, okay? So thank you.